Welcome to our lecture on Lagrangian mechanics. Today, we'll explore this elegant reformulation of classical mechanics developed by Joseph Louis Lagrange in the 18th century. Lagrangian mechanics provides a powerful alternative to Newtonian mechanics, especially when dealing with complex systems with constraints. Let's start by understanding some key concepts. First, we have generalized coordinates, denoted as q sub I. These are any variables that can describe the configuration of our system. Unlike Cartesian coordinates x, y, and z, these can be angles, distances, or any parameter that uniquely specifies the state of our system. For example, we can describe the position of a pendulum using just the angle theta instead of x and y coordinates. This simplifies our analysis significantly. The central concept in Lagrangian mechanics is the Lagrangian function, denoted by the letter L. It's defined as the difference between the kinetic energy T and the potential energy V of the system. So, L equals T minus V. For example, in our pendulum system, the kinetic energy is 1/2 mL squared theta dot squared, where m is the mass, L is the length, and theta dot is the angular velocity. The potential energy is mgL times 1 minus cosine theta, where g is the gravitational acceleration. Therefore, the Lagrangian for the pendulum is 1/2 mL squared theta dot squared minus mgL times 1 minus cosine theta. Next, let's talk about the action, denoted by the letter S. The action is defined as the integral of the Lagrangian over time, from time t sub 1 to t sub 2. Mathematically, S equals the integral from t sub 1 to t sub 2 of L dt. This brings us to the principle of least action, which is the cornerstone of Lagrangian mechanics. It states that the path taken by the system is the one that makes the action stationary, which usually means minimizing the action. If we visualize different possible paths a system could take, the actual path taken is the one that makes the action stationary. To find the equations of motion in Lagrangian mechanics, we used the Euler-Lagrange equations. For each generalized coordinate q sub I, the equation is as follows. The derivative with respect to time of the partial derivative of L with respect to q dot sub I minus the partial derivative of L with respect to q sub I equals 0. This might look intimidating, but it's essentially telling us how the system evolves over time. It's a second-order differential equation that gives us the equations of motion. Now, let's work through a classic example, the simple pendulum. This will help us see how Lagrangian mechanics works in practice. We have a mass m attached to a massless rod of length L, swinging without friction under gravity. We'll use the angle theta as our generalized coordinate, measured from the vertical. Step 1. Let's find the kinetic energy of the pendulum. The velocity of the mass is L times theta dot, which is the length times the angular velocity. So, the kinetic energy T equals 1/2 mv squared, which gives us 1/2 m times L squared times theta dot squared. Step 2. Now, let's find the potential energy. We'll set the potential energy to 0 at the lowest point of the pendulum. The height h above this lowest point is L times 1 minus cosine theta. So, the potential energy V equals mgh, which gives us mgL times 1 minus cosine theta. Step 3. Now, we can calculate the Lagrangian, which is T minus V. L equals 1/2 mL squared theta dot squared minus mgL times 1 minus cosine theta. This simplifies to 1/2 mL squared theta dot squared minus mgL plus mgL cosine theta. Step 4. Now, we apply the Euler-Lagrange equation to find the equation of motion. We need to compute the following derivatives. The partial derivative of L with respect to theta dot is mL squared theta dot. Taking the time derivative of this, we get mL squared theta double dot. The partial derivative of L with respect to theta is minus mgL sine theta. Putting these into the Euler-Lagrange equation, we get mL squared theta double dot plus mgL sine theta equals 0. Dividing by mL squared, we get the equation of motion, theta double dot plus g, over L times sine theta equals 0. For small angles, we can make the approximation that sine theta approximately equals theta. This is known as the small angle approximation, and it's valid when theta is small. With this approximation, our equation of motion becomes theta double dot plus g over L times theta equals 0. This is the equation for simple harmonic motion with angular frequency omega equals square root of g over L. The period of the oscillation is t equals 2 pi times square root of L over g. Let's see this in action with our pendulum. If we release it from a small angle, it will oscillate back and forth with a period given by this formula. Let's discuss some advantages of Lagrangian mechanics. First, it works with any set of generalized coordinates, making it ideal for systems with constraints. Second, it's often simpler than Newtonian mechanics for complex systems, especially when there are constraints or when the system is most naturally described in non-Cartesian coordinates. Third, it provides a pathway to more advanced physics, such as quantum mechanics and field theory. Finally, it elegantly reveals conservation laws through symmetries, as described by Noether's theorem. To summarize what we've learned today, Lagrangian mechanics is based on the Lagrangian function L, which is the difference between kinetic and potential energy. The principle of least action states that the path taken by a system is the one that makes the action stationary. The Euler-Lagrange equations give us the equations of motion for the system. For a simple pendulum, the equation of motion is theta double dot plus g over L times sine theta equals 0. Under the small angle approximation, this reduces to simple harmonic motion with a period of t equals 2 pi times square root of L over g. Thank you for joining me in exploring Lagrangian mechanics. I hope this has given you a good understanding of this elegant approach to classical mechanics.